Hey, this is Leach with Simpson Math, and in this video, I'm going to talk about what a real number is and all of the different sets and subsets within the real number set. And then also, we're going to be taking a look at an example on 2.1 in my contemporary 1332 class. So first, actually, I just want to pop open with my camera here. So let's talk about what a set is. So when I think of a set, I just think of a little box, a container. So here I have this box. Notice right now it's empty, just an empty box. I would refer to this little box as an empty set. It's a set. It's a container. It just has nothing in it other than air. I'm not considering air a thing. So this would be an empty set, and we'll talk about the notation. We'll see the notation for that in a second. But I might have other things. So here's I've gotten into crochet recently. So here's a little coffee mug I made. Here's a little dog bowl and bone, a little fox that I made. This is the body of a of a dragon that I'm working on. I also have like little enamel pins I made. So here's like a little cutie pie. Let's put that in there. So all these things are in this box. So that was a set of those things. So there was a set of these little crocheted items, and also one of my enamel pins that I made. So this is now a set holding those things. We have something called a subset. So if I was to, I could imagine this set. So this is my full set. Everything but one of these things was crocheted. So all these things in here, if I take out this thing that isn't that, if I kind of consider, or just kind of like ignore it, let's just kind of put it here and ignore it. I have a subset, a smaller collection of things that are just the things that are crocheted. At the same time, I could also have a smaller collection of things that are ignoring the crochet things. I would just have this. That would be also a subset. Subset is a smaller one. You could kind of consider that like a box within a box. Here I have a box of straight pins. If I put that box of straight pins inside of this box, well, then I have a big box, which is my set of all these things. And then inside of that set, I have another smaller set, which is a set of all of these push pins. So that's that idea. So a lot of kind of vocab that we're needing right up front. All right, let's talk about the real number set. I'm actually going to start at the bottom of this real number set. And we're going to be talking about natural numbers. So kind of historically how we came about with this first. So first, way long ago, like at the beginning of human history, we like to compare things. It's like, oh, I have 3 goats and you have 5 goats. When I'm counting my goats, I'm going to start counting with 1, 2, 3, 4, so forth. That's the natural numbers. 0 is not part of that. They're only positive. They're counting numbers. And vocabulary-wise, we refer to that as a natural number. All right. Then, if I add on a 0, that's the only difference between whole numbers and natural numbers, is that we have this 0 here. So whole numbers also include the 0, which took a long time in human history for us to kind of get around to dealing with 0, to have a number to represent nothing, because it's like, well, if I have goats, I'm going to start counting at 1, 2, 3. If you don't have any goats, we just didn't have a number to represent that. So that's the only difference between these two. All right, then maybe we're talking about needing to, borrow goats, or comparing goats. So, I might have 3 goats and you have 5 goats. So you have 2 more goats than me. So there's a difference of 2. But we could start thinking of negative numbers, or I have 2 less than you. So maybe in that way that we then end up with those negative numbers. So, and then naturally we then would need some sort of way for 0 to be in the middle. So notice that whole numbers and natural numbers don't have negative numbers, but the integers do. Real fast, I haven't been talking about these on the side. That's just a shorthand that we do. I don't think in my contemporary 1332 you'll see those show up, but we can shorthand integers with a big capital Z, but we're a little bit extra mathematicians sometimes. So we kind of basically represent it as a bolded letter, but a special kind of bolding. And so we kind of make it be this double bar Z. We kind of make it look like it's extra thick by drawing those double lines. So a double bar W is the whole number set, and a double bar N is the natural number set. All right, well, then at some point, especially if someone has like a lot of goats, So, I might only have 5 goats, but then that person over there has 20 goats. So not just that they have 15 more, but that they have 4 times. So we start kind of being able to compare that in terms of a ratio. Or from maybe their perspective, instead of them having 4 times the number of goats, I only have a fourth. I only have 1/4 as many goats. So I have this kind of ratio comparison. So look at this word here, rational. And you should see broken down in the middle of that is ratio, or the beginning of it is ratio. Ratio, I don't think of ratio, I think of fractions. Ratio is kind of, it's a division process, a concept. Even like if you look at the word ration, I imagine in some kind of dystopian society, or maybe, I don't know, you're stuck on a ship in the middle of nowhere. You have your daily rations. You only, we have this much food, this many people, this many days. So divide. Everybody gets this much. This little ration, this piece of the total food. So that fraction. So notice every number we've talked about so far, natural numbers, whole numbers, integers, all of those can be written as a fraction. So that 4 that I talked about is just 4 over 1. 0, for that matter, is also 0 over 1. Notice 0 over 1 is 0. 1 over 0 is something called undefined. These negative numbers, negative 2 over 1 is a fraction. So all of those numbers can be written as a fraction. But now we have a collection of a few more that are not integers. So here we have 2/3, which as a decimal we would write that as 0.6 with a bar over it because it goes on forever and ever and ever, but it can be written as a fraction. And then we have something like 1/4, where its decimal terminates. It terminates at 0.25. I don't just write a whole bunch of zeros. It just ends at 0.25. So both of these are numbers that can be written as fractions. One note about their decimal versions. Decimal versions of fractions, their decimals will either start repeating, they'll hit some sort of pattern that it repeats, or it terminates. If I come across a number that actually cannot be written as a fraction, that might be a little bit hard to see on your screen, but it's the word irrational. Write it out in not yellow. What was I thinking? And then highlighted it in yellow. So the word irrational, which we represent with the double bar I, for irrational, and notice this was a double bar Q. Q for like quotient idea. So these are numbers that cannot be written as a fraction. So famously, pi, like where'd my cutie pie go? This is one of my pi pins. It's a cutie pie. So that is an irrational number. Square root of 2. I like to think about square root of 2. I'm going to ramble for a second. So if I have a number line here, here's 0, here's 1, here's 2. Let's say I have another number line going vertical, 1 and 2. This distance here, using some geometry we learn, is square root of 2. So if I let that fall down, it lands at square root of 2, which is about 1.41-ish. But if I keep looking at all those decimal places, it's never going to end, never going to repeat. It's just going to be square root of 2. It's just some decimal that just never ends, never stops. It goes and goes and goes forever, like pi. There's something called e, cube roots, etc. So there's a whole lot of those. So if it's a rational number, it is never, ever, ever irrational. If it's irrational, it's never, ever, ever rational. But the rational set is broken down that there are some rationals that are integers. Those are the ones that have a divided by 1 in their denominator. Then there are integers that are whole numbers. We're getting rid of those that are negative. And there are whole numbers that are natural, and that's all the numbers except for 0. So that is what we call the real number set. So all of these are sets. So I'm talking about my subset idea, that the rational numbers is a subset of the real number set. Irrational is a subset of the real number set, but you can almost kind of think about it as just a cleaving. There's a splitting into, not in half, but these don't interchange. But in terms of subset, integers are a subset of rational, whole numbers are a subset of integers, and natural numbers are a subset of whole. They're also a subset of integers. They're also a subset of rational. All right. So let me switch over to a question. It's question 5 on 2.1. So this is popping up in our first homework assignment. And so we're just going to do a little bit of matching. All these are talking about integers. Some of these could use some different vocabulary. I don't think in this course you'll see irrational popping up, but you will see in this 2.1 homework, you'll see the word integers, whole, and natural used. So we need to make sure that we are good with that terminology. All right, so just in terms of this problem, when you pop it up, you're like, where's the other thing? You need to click on this to pop open. It says click on this icon to view the table. And then these pop, anytime you see a pop-up, you can actually move them where you want to, so you can kind of get them out. They can't leave the window of MyLab, but you could even like scooch it off to the side. I can't see it off the edge, obviously, but I can move it out of the way. All right. So if you're also curious, why is it 5 through 12? In the corresponding problems with the textbook, 2.1, 5 through 12, if you were to look in the book and flip over to the homework in 2.1, you'll see these questions or a version of these questions living over there. All right, so let's play a little bit of a matching game. So I see the numbers 1, 3, 5, 7, 9. Which of these best help me out? Best match that? Well, let's read our A through H's just so that way I can see. So this first one, this is a set of all even numbers. That sounds like a whole lot more than this, and those aren't even. The set of the 5 least positive integer powers of 2. Ooh, powers. Oh, that's not what this is. We'll talk about that. The set of even positive integers less than 10. Well, those aren't even. The set of all odd integers. Ooh, these are odd integers, but I don't like the word all here because it's just the first 5. The set of all negative integers. Those aren't negative. The set of odd positive integers less than 10. Seems like it's going to be the answer, but I'll hold off for a second. Let me finish reading G through H so we get familiar with the whole set. There's this weird symbol. This weird symbol is the symbol for the empty set. Let me also talk about what other symbols for the empty set. So the empty set that was talked about when I just had a box with nothing in it. So the empty set. There's a few ways, 2 primary ways to write it. You'll see, like here, like you see on the screen, where we saw a second ago, it's basically a 0 or more like a circle with a slash through it. This is why math people, at least the math people I know, we don't like it when students write like the number 70 and they slash it, or just the number 0 and they slash it, because that 0 with a slash implies the empty set. So it's not 0. If you just see an empty box, that box isn't 0. That box is empty. Another way that we write the empty set is we'll just open with our set notation. Like you see that all of these on the screen over here, they have it starts with a set bracket and it puts something, and then it ends with a set bracket. So this it kind of goes like this. That's how we do the set brackets. So, but specifically oh, sorry, that closed in a parenthesis. That was weird. But if we see a set bracket that we open and then we close and we have nothing in it, that's called the empty set. Let me draw those a little bit neater and bigger so we can see that. So the empty set, we have a set bracket like so, and then it closes like so. So that would be the empty set because I open my set, close it, and there's nothing there, or this circle with the slash through it. All right, then lastly, we have the set of the 5 least positive integer multiples of 2. All right, so as we're reading through this, F sure sounded right. The set of odd positive, these are odd, they're positive, and they're less than 10. So let's say that this is F. All right, then now there's this interesting little X and a line. I read that as this is the set of X, that vertical line, we read that as such that. So it's the set of X's such that, or where, or, ooh, let me provide my condition. So in math, we will often do, we'll have our set. So it says the set of X is such that, and I might say X is greater than 3. This is not what this problem is, but I would read this as the set of X, of whatever I'm looking for, and then such that, and then my condition. In math, we like to write what we're looking for first, given such that some sort of vertical line. Also, you might have heard this as, like I said, as given or where. Any of those things are kind of common uses for this vertical line. And then we list out our conditions. So in this particular question, we have this is x such that x is an integer greater than 4 and less than 6. Greater than 4 and less than 6. Well, let me get my iPad back up here. And if I have a number line, and here's 0, 1, 2, 3, 4, 5, 6. Let's do a few more, 7 and 8. Well, I need greater than 4, not greater than or equal to, so greater than 4, so greater than 4. So this could be, they do say integer, so this could be 5, 6, 7, or 8. Or less than 6. So less than 6, so not touching 6, but less than, so that could be 5, 4, 3, 2, 1, 0. But it does say even, an even number. So not 5 or 7 or 3 or 1. So it would have to be some even number. And notice, bigger than 4, even number bigger than 4 would be 6, 8, 10, 12. Even number smaller than 6, not counting 6, would be 4, 2, 0, so forth. So notice how there's no number that represent this. So that's why this is going to be the even set. Sorry, I misspoke, the empty set. So that letter G. All right. This one, do you see this this dot, dot, dot? The dot, dot, dot is an ellipse. The ellipse just means let it keep going. It's how the vocabulary term for the dot, dot, dot. But it's an ellipse, so we're just going to keep going. So my brain, I'm kind of starting at -1, going back to 2, back to -2, back to -3, back to -4, on and on and on down. Or, in terms of least to greatest here, we're going from -infinity all the way up to -1 and stopping. So these are all negative numbers. They're all integers. So that looks like the set of all negative integers. We don't have a special vocabulary term for negative integers, like whole numbers or natural numbers are the positive integers. Whole numbers are the non-negative integers. Negative integers are just negative integers. They don't have a special name. So this would be E. All right, then this next one. So from -infinity, then we're going from -5, -3, -1, 1, 3, 5. Those look like those are all odd. Those are odd numbers. And since I'm going to -infinity, and then going to positive infinity, that looks like all odd integers. So that's going to be D. All right, this next one, I have 2, then 4, then 8, then 16, then 32. Those are all even, but it's not all even. And 1, because I don't have a dot, dot, dot. 2, notice, where's 6? Where's 10, 12, 14? So it's not a certain even. This is actually the power situation. So let me remind you about a power. So 2 to the power of something. So if I have 2 to the power of a first, 2 to the first would be 2. If I have 2 squared, that would be 2 times 2, which is 4. 2 cubed, that would be 2 times 2 times 2, which is 8. So reminder about what it means for an exponent, to how many times you multiply that thing by itself. So multiplying 2 by itself 3 times. 2 times 2 is 4. 4 times 2 is 8. So we can keep that pattern going. 2 to the 4th would then be that 16. 2 to the 5th would then be the 32 that we're getting there. Oops, 32, not 36. One note, just because this might show up, anything raised to the 0 power is actually 1. Look, we can kind of verify that here. Notice when I went 2 to 4, 4 to 8, 8 to 16, 16 to 32. Notice it's a times 2, times 2. I'm just multiplying it times 2 every time I move. Every time I move further and further up, it is a times 2 situation. That means if I was going the other way, it would be a divide by 2, divide by 2, divide by 2, divide by 2, divide by 2. Well, that means if I go from 2 to 1, I should keep that pattern up, which is a divide by 2. Notice we get 1, right? So 2 to the 0 power is 1. Not that we need that for this problem. That's just a nice FYI thing. And so that's what we're going to do. That's what we're doing. The set of the 5 least positive integers. Oof, that's a little mouthful, but let's talk about that. The 5 least positive integers. That's why if I pop this back up, we get 2 to the first, 2 to the second, third, fourth, fifth. 1, 2, 3, 4, 5 are the 5 least, as in smallest, positive integers. Notice 0 is not positive. It's neither positive nor negative. It's between those two. And -1 would be negative. So these are the 5 smallest positive integers. And again, integers because they're not decimals. They're not 1.1. It's just 1, 1.0. Or the denominator of it is 1. All right, so this one is, let me get this off. B goes to number 9. All right, I see on 10, I see ... from the left to the right, and I see that they're all even, and they're all integers, so it's a set of all even integers, kind of like the odd one. Then I have 2, 4, 6, 8, 10. Those are even. And so which ones haven't we used? So we haven't used A, B, C, C, D, E. We haven't used C or H. So the set of even positive integers less than 10, or the set of the 5 least positive integer multiples of 2. Well, okay, so less than 10, does less than 10 include 10? Nope. So the even positive integers, so even positive integers would be 2, 4, 6, 8, 10, 12, so forth, forever, but starting at 2, going to infinity, so it would only have a ... on the right side, not the left. It would be basically number 10, but the ... the -4, the 0, and the 2 would be gone. So it's 2, 4 on to infinity. So it's those ones that are less than 10, so the ones not including 10. So I'm going to go ahead and jump to 12 and say that's C. Now, again, this H uses the 5 least positive integer multiples of 2. So we have the 5 least positive, so that's the smallest 5, but not starting at 0. But multiples of 2 is another way of saying even. It's a multiple, that means I can skip count. 2, 4, 6, 8. Because if I start at 2 and then start skipping, add 2, add 2, add 2. Or multiply, because if I do 2 times 1, it's 2. 2 times 2, 2 multiplied by 2 is 4. 2 multiplied by 6 is 3. 2 multiplied by 4 is 8. So multiples are the skip counting, or the how many multiple 2's can you have every time you add an additional 2. So that would be that H. All right. So in this particular question, I don't think it doesn't do a randomization. So if you do your check your answer, you'll be able to, it'll say that you're right, which is excellent. There's not, this one in particular doesn't have like a similar question because that question just is. But I just want to show you because this is the first one. I have a teacher button that says show completed. Sorry, you don't. But notice on this question that says the set of all counting numbers less than or equal to 9. Counting numbers is another vocabulary term for natural numbers. Counting numbers are natural numbers. If I press similar question, it's a similar question, all counting numbers but less than or equal to 3. Pro tip, if you highlight the question and then there's something that doesn't highlight, it's because it's what changes. So this 3 is what changes from question to question. So notice it was 9 a second ago, now it's 6, now it's 3, now it's 2, now it's 8. So those are the things that change. I say that just to kind of make your life a little bit easier. Try to avoid using this as just pattern recognition. Some students will, again, they just try to view the homework as a thing to get through, not the learning experience. If you don't know why the answer is this, you just recognize the pattern. And so you just did it. Like if there are vocabulary terms that you don't know, then you need to ask. Go to the textbook. Do the view an example. Do the help me solve this. So make sure to do those things so that we can be successful. So even after you finish the question, you could be able to press a similar question. So let me do this one from scratch. Express the set using set notation and the listing method. So less than or equal to 4. So that would be, these are counting numbers. So that starts with a 1, 1, 2, 3, 4. I press check answer. It'll say excellent, good job. But if I go back to it, well, I'm in teacher mode, so sometimes it might not, but you should, for you would be able to go back to it and then do a similar question, like it would look like here. All right, hopefully then that's helped help you understand a little bit about the real number system, and then kind of to get started on the homework. So that one was kind of weird and daunting, so I wanted to do that with you. Hope this helps, and I will see you in the next one. Bye.